Thank you very much, and thank you to the organizer for such a beautiful event and for inviting me to talk today. So here on the blackboard, you can see an object you were probably very familiar with. So this is a sum to Feynman diagram to double box. And on the right-hand side, you can see a pictorial representation of an amplituhedra whose canonical form will give us the amplitude corresponding to the sum of this Feynman diagram. So today I would like to talk to you about some work in progress that I have with Elia Mazzucchelli, who is a PhD student of Johannes Henn, and Felix Delander, who's a postdoc at Oxford in the group of Eric Panzer, about exactly this geometry here and its connection to this amplitude. So even though this is from many point of view, is a pretty basic amplitude, given also the fact that we are not talking about the integration here, but just about the integrand. It has some very unexpected feature that have emerged in the past year, that it makes the perfect toy model to kind of explore the differences between the geometrical feature that we observe in a tree-level amplituhedra, and that is the analytic property that we see in tree-level amplitude, and a new feature that appear at loop level. So the most important concept in this game is the canonical form. So the canonical form, it's a map from a space of oriented regions to a space of differential forms. Of course, it's a space to some specific class of oriented region to a specific class of differential form. These differential form are in particular D-log form. And D-log form are pretty much characterized by their residues under certain condition. And we will have roughly that some physical quantities that can be written as D-log form, we will be able to write them as the canonical form of some region. And when this is possible, we'll call this region positive geometry. Now, the most fundamental property of this canonical form, and that also defines it, is that it connects operation on cohomology to operation in homology. So we have that the residue on an irreducible variety Ci, will may be more specific later, of the canonical form X, is mapped to an homology operation on the other side that is called the partial boundary on the variety Ci. Okay. So we are interested in study what is called the boundary stratification of the geometry. Okay. Geometry. Okay, so this is a kind of separate thing. Like, you know, when you integrate, you have a pair between two objects. An integration path, that usually is kind of some homology object, and a form that you are integrating, that lives in homology. Here, what I'm doing is mapping what you have to integrate, the integrand, that is a form, connecting to some region, right? So when you will have an integral, usually you have a pairing between some region and something in homology with something in cohomology. Thanks to this math, you can also think this as two, when you integrate something, like two region. One will be your integration path, and one will be your integrand. Okay. So like a classical example is like the d logarithm. You have the integral over like a simplex of a form that is the canonical form of a simplex. So you can think the d log as a pairing between two triangles, essentially, thanks to this map. I don't know if things make it clear, but short answer, this is about the integrand, not the integration path. Then you will have to specify the integration path. Okay? Good. So, no, I'm saying that, here I'm saying that I have an operation defined in cohomology, there is the residue, okay? And now I can do an operation on the homology side that is taking a boundary, okay? And I can connect the result. Like it's an homomorphism between like operation and the two spaces, right? Okay. So in another word, like if I want to take a residue, what I can do is like take a boundary on the geometry and then compute the canonical form. I can invert the order of this operation, and the way of doing it is to do this operation defined here. So what we're interested in study the boundary stratification, that is the successive application of this boundary map. And on the side of the cohomology, this means compute all possible residues. And it's the omega is the map that goes from a region and give you the canonical form, which is a form. Okay? Then you can give this a name, small omega, and you'll be your form. Right. No, in this case, I'm using big omega as the map between these two spaces. Differential form on the space will be an irreducible variety. In an irreducible variety will be the ambient space of the differential form. Okay. I will be more specific later. This is just a general picture, let's say. Okay. So when we want like even to test like if something is the canonical form of some region, what you should do in practice is do these two operations on the both sides and see that things match. You have your form, you compute all possible residue, you have your geometry, you compute all possible boundary, and you see that the two things match, especially at the lower level. The maximal residue will be number, and also the result of the applying this boundary operation until you go to the smallest geometrical object that is a point will be a number, and these two numbers have to match. Okay, so what's so this type of geometry as being considered in the past, and actually it was really, I think, the third paper on the amplituhedron. So I will indicate this geometry as A402. This means that this is amplitude at 4 point. This is the NMHV degree. This is 0, and 2 is the number of loop. And these people have been, this geometry have been studied by Franco, Galloni, Mariotti, Trinca in 2014, with a follow-up in 2016 by Galloni. And the aim of this author was to study all possible boundaries of this geometry and then compute the Euler characteristic. Okay. What does the second number stand for? Number of loops. The NMHV degree. So amplitudes in n equal to 4 are grouped by NMHV degree. That, roughly speaking, is the number of negative helicity gluon in your amplitude minus the number of positive helicity gluon. Okay, but this works is incomplete in some sense, because there are subtleties that appear, and so there is boundary that have been missed in this computation. And there's also a subtlety in the computation of the Euler characteristic, which made like the result essentially invalid. And I will try to clarify what's a way to systematically compute these boundaries, so do not miss, be sure not miss anything, and what's like the correct way of computing the Euler characteristic in this case, where the topology is not trivial. So in previous example of positive geometries, almost always the geometry was isomorphic to an open ball, and these subtlety were not appearing, and this is the first time that they appear. So I would like to sketch exactly what are these features. So whatever happened with the time, you will have an idea of what these things are. So the first thing is that this geometry presents something that's called internal boundaries. That is something that has been observed for the first time last year by me, Heslop, and Stewart. So 2023. And this feature is called internal boundaries, and I can give you a very simple example of what it is. So you start with a geometry that is, whose interior is disconnected. Then you want to compute how the boundary of this geometry is, and you can do it by thinking really as a union of two triangles. We know to compute the boundary of a triangle, this is a segment. In particular, it is an oriented segment. So this one will be oriented this way. This triangle has the same orientation, but is on the other side of this line. Therefore, the induced orientation here will be opposite. And the result, it's a big segment, but the induced orientation has a discontinuity in the middle point here. Okay? So this geometry has a boundary on this point here. We call it internal boundary because crossing it doesn't really take you out of the geometry like is it in this case for this point. And from the point of view of the differential form, it means that here we will have a non-vanishing residue. And this is exactly what has been missed in this original work here, both from the point of view of the geometry and from the point of view of the form. This becomes as a kind of non-trivial factorization in your denominator that have been missed. And when this factorization happens, you have multiple choice for taking your residue, and it's, if you don't have a systematic way to proceed, it's kind of easy to miss. Now, right. The orientation is induced from the inside, so you could have different geometry, where you have a different orientation, and this point will not be a boundary of the geometry. Right. Good. So I would like to give you a brief summary. It was like the state of the art for 3-level geometry. So 3-level amplituhedron. So the starting point was the positive Grossmanian, GR K, N, which is a space of plane, K-plane in n dimension, and it is a subspace of the oriented Grossmanian, which is the space of oriented plane in K. Sorry, this is a space of called the positively oriented K-plane n dimension, and this is the space of oriented K-plane in n dimension. And so the story here is that the boundary structure of this geometry here is extremely complicated and subtle, but by the work of Postnikov, essentially in 2006, and other people, but mainly him, we have a complete understanding of all the boundary structure of this geometry and a very good control on all its property and also how to compute all the boundaries. So here we have correspondence between boundaries and something called Plabic graph, or in our community, thanks to the works of Nir Markani Hamed and Jake Bergili and other people on shell, many other people, shell diagrams. And, sorry, I don't have much space here. And varieties. Class of varieties called positroid varieties, and we know all their properties, if they're singular, if they're not singular. And therefore, the positive Grassmannian story was, it's really under control. And this, as many people in this audience know, this is the seed for the definition of the amplituhedron. So roughly speaking, the amplituhedron is a projection from the positive Grassmannian. There is one very nice example of it. There is a toy model, but it's also like a true amplituhedron. So the tetrahedron is an amplituhedron. And we can take a projection to 2 dimension. And in this projection of the tetrahedron, it will become a square. Now, this will be the amplituhedron. This will be the positive Grassmannian. But there is another very nice feature of this projection, is that if I take some 2-dimensional boundaries of the tetrahedron, let's say, for example, this 2 triangle, I get a triangulation of the square. So from the knowledge of the boundary structure of the amplituhedron, you can derive a triangulation for, sorry, from the boundary structure of, knowledge of the boundary structure of the positive Grassmannian, you can derive what is a triangulation of the amplituhedron. Any 3-level amplitude in n equal to 4. Okay? And this was conjecture by Niamar Hamed and Trinka, but to make this statement precise was like a big effort of the math and physics community of the last 10 years. So for the 3 amplituhedron, we have worked by Tomek for the m equal to 2 amplituhedron, which correspond to 1 loop MHP amplitude, but also like is more general than that. And then we have a series of work by a group of essentially mathematicians, Evan Zohar, Williams, Tesla, for the m equal to 4 amplituhedron. And this series of work is extremely recent. It's like the last 2 years, where they proved that indeed you can use the boundary structure of the positive Grassmannian to triangulate the amplituhedron. And also they kind of give us a lot of information about how to use the boundary stratification of the positive Grassmannian to study the boundary stratification of the 3 amplituhedron. And then M is a parameter in the definition of the amplituhedron that for physical cases is 4, but then the amplituhedron is more general than that, and you can have M can take different values. Physically is the dimension of the twistor space. Yes, but not directly. It's for like dimension 6 is not 6. Then there is also a story of the momentum amplituhedron. That is the amplituhedron in spinor helicity variables. And this appears in for n equal to 4, but also for the n equal to 3, n equal to 6, ABJM, thank you. The name was not coming. And also there, we have a very good control over the boundary structure of this geometry with very refined combinatorial tools that was completely non-obvious from the positive Grassmannian. And the authors of these works are pretty much all present in this room. And recently, there's come also work from some mathematician for the one loop amplituhedron from Ranestad, Sin, and Tellen. And what is interesting about these works is that they don't really use the fact that the amplituhedron, three amplituhedron come from the projection of the positive Grassmannian. It gives you a lot of great tools, but it's very constraining. If I have a general positive geometry that's in some other theory, or let's say I have another amplitude in another theory and I want to try to repeat this type of computation, I cannot use all the powerful tools the mathematician have developed for the positive Grassmannian, but I can use some of the technology of this group of people developed for tackling this case. Okay. So let's have a look at the one loop 4-point case, aka the massless box. And let's see how the situation is in that case. So A401 is the massless box. And in Twister's variable, it will look something like this. It will all be a product of these momentum twistor brackets, which are determinants B23, AB34, AB14. Then we'll have a bracket 1, 2, 3, 4 square the numerator, and then we will have a measure. Sorry why I'm doing this. DA, DA, AB, DB, and DB. This is a kind of a neat way of writing a measure in the Grassmannian GR, 2. So we'll have the object that we have here are momentum twister, which are points in P3. Okay, so they look like I is 1, dot, to ZI4, modded by GL1. So these are two momentum twister are equivalent up to rescaling. And then we have the loop degrees of freedom will be captured by an element in GR2, 4, which instead is a matrix A1, A4, B1, and B4. So it's a 2x4 matrix. A line essentially can be captured by 2 points, but then I can slide this point along the line and will identify the same line. So the 2 point AB will be identify the same line if I multiply AB by a matrix M, where M is in GL2. So, and then these brackets here are nothing by determinant of 4x4 matrix. So 1, 2, 3, 4 is equal to the determinant of the matrix made by Z1 up to Z4. And the matrix here, ZI, AB, IJ is equal to the determinant of AB, ZI, Zj. And similarly for the measure. Each entry is a vector, some are the differential of a vector, and then I take the determinant, and that's the form. Does it make sense for everybody? So, exactly, like to see how many degrees of freedom we have for the loop. So naively here we have 8 entries in the matrix. So we have 8 degrees of freedom, but we have to mod out by GL2, which is 4 degrees of freedom. And so we are left with 4. That is the usual 4 degrees of freedom of a loop in 4 dimension. Well, okay, like if you have an amplitude that is an massless amplitude that is function of complex momenta, you will have like 3 complex degrees of freedom or 6 real degrees of freedom for each. Yeah. Exactly. Like you should have decide what's if you want to be in the physical region or. But of course, is to get a grasp to do practical computation with this moduli space. So this kind of a moduli space description of the Grassmannian. We can fix the gauge somehow. So we can, for example, choose the Z matrix made by Z1, Z2, Z3, Z4 to just be the identity. And we are free to do this because everything that appears is a determinant, so the whole formula will be a GL4 invariant. There's a global GL4 symmetry, which allows to fix us the Z to the identity. And then we can choose to parameterize the loop as follow. Y, Z. And in this parameterization here, the form takes this very simple form that is just the d log of all the variable that I have. So d log x, d log y, d log w, and d log z. Okay. So now I told you that I would like to study all possible boundary of the geometry, and on the cohomology side, I would like to study all the possible residues of this form, right? But in these coordinates, you will see that this becomes impossible. But before do that, let me define what a residue is. Okay, so to define a residue, first, we have to be precise about with our ambient space, as David was asking before. So we start with an ambient space that is a variety, X. So what's a variety? Is just a space. We will be interested in complex varieties. So we have an element in Cn, and we are looking at all the Z that are a solution of some polynomial system of inequality. Pnz equal to. Sorry? Yes. So the external kinematic here, you have an amplitude that is dual conformal invariant. At 4 points, essentially, the dual conformal invariant allows you to fix all the degrees of freedom. There are no cross ratios at 4 points if you are in the like limit of your kinematics, essentially. This is the statement that an amplitude and dual conformal amplitude of 4 points doesn't have any degrees of freedom, and so the amplitude is just a function of the coupling, if you like. So GL4, it is really a representation of the dual conformal group, precisely, the complexified dual conformal group. Okay, so we have an irreducible, we have a variety. An irreducible variety is an X such that it doesn't exist two subvarieties X1 and X2 contained in X, such that X is equal to the union of X1 and X2. And this is the avatar of what happened with polynomial. Like an irreducible polynomial is a polynomial that cannot be written as a product of two polynomials. Okay? So before I give you the definition of the Grassmannian as a moduli space, but the Grassmannian can also be described as a variety. So you can forget about all these matrices and things, and just take this AB, IJ as your coordinates, and then remember that these coordinates are not independent. There is a relation between these coordinates that is the so-called Plucker relation. AB 34 plus AB 14 AB 23 minus AB 13 AB 24. And this is a definition that computer like very much. And also notice that this equation is homogeneous in these coordinates. So I can essentially rescale one of the coordinates to 1 without losing generality. So this is not just a variety, it's an inducible variety, and it is a projective variety. That is, all the polynomial equations that define it are homogeneous polynomials. Okay, good. So our amplitude, we discovered that is a form defined on a variety. Now, we define what is a simple pole. So a simple pole is when I have a form that I can write it in this form. So I have a d log of an irreducible polynomial with something plus eta, where these two objects here must be regular on pi going to 0. So they must not diverge. And then we can define a residue. So there is a correspondence between polynomial and irreducible varieties. So if I have a polynomial pi, I can associate an irreducible variety ci. And I want to define residues. Maybe it's better if I wrote it on another blackboard. So the residue on ci, that is when pi goes to 0, of the form omega will be equal to psi restricted on ci. As I actually learned from a paper of in Root on residues and cuts. And this reduction, I have to tell you though what it means, this reducing to a variety here. And there is a kind of two way of thinking about it, which I've been discussing with Tomac and Livia and his group recently. So one, I will say that most people in our community used in practice is to think this as the pullback of psi to ci. But there also another way that apparently is more common amongst mathematicians, is just to think this as an equivalence relation. So psi is equivalent to psi I if psi x is equal to psi prime of x for all x in ci. And the other, so omega is defined on x, that is an irreducible variety, and then we will get a form that is defined on the whole space, but it has an equivalence relation. So effectively, it is defined on just the subvariety ci. Okay? Yes. Right. So the advantage of this definition is it's very practical for computation. The advantage of this definition is that the residue of a rational form, it is always a rational form. Okay? And I can keep using the same definition of a residue that I had before and compute like multiple residues. If I have instead this, if I use the pullback, I can have like square roots appearing, and it will not be, that definition essentially will be confusing because I cannot, I want to factorize just a d log of a polynomial and not having like, and have the other things regular and not to be able to do that essentially. But this is like not the, really not key things for what we are saying later, but I think it was a nice thing to say because it was a thing that was confusing in our community for a bit, like why the residue, for mathematician, a residue of a rational form, it's always a rational form. It is because they have this different definition of a restriction. Eta is like just fixing your representative in the class, right? So you can choose different eta and have different representatives. So now let's, exactly, like where eta vanish on, eta is any function that essentially is like pi times something, no? So it's proportional to pi. Exactly. So if you do the pullback of these two things, you will get the same thing. This is why these two definitions kind of make sense to coexist. So now let's go back to this form here, and we'll compute residues. So we see that the form is already written in a very nice form to compute residues. Okay, we can take like a residue in x equal to 0, and this would be simply like d log of y, d log of w, and d log of z. The problem is that if I think about all possible multiple residue now, right? So what I can do is just changing the order in which I set this thing to 0. So I have like 16 factorial. It looks naively that I have 16 factorial possible residue I can take. Here is the situation is quite trivial, so they all look alike. But the thing is, the actual number of possible multiple residue that I can take is of the order of 100. The point is that in this patch, I can just see one subset of the possible multi-residue. Another thing that you can notice is that we know very well that the maximal cuts of the box where all the propagators are put on shell are 2, right? And here we just see 1, where all x, y, w, and z are equal to 0. And in fact, you can see that in this parameterization, we have this thing fixed to the identity. So this thing fixed AB24 to be -1. And therefore, whatever maximal residue we take in this coordinate, we will never be able to set AB24 to 0. So it's just this usual thing that we have a patch, not everything is visible into the patch. So how we can proceed in like a more covariant way without the needs of fixing coordinates. Okay, this is essentially what I want to say. And the answer is to think really about our denominator as a variety and compute what is called the canonical stratification. Canonical stratification. Okay, so we have a form. We'll have some irreducible polynomial denominator, a numerator, right? To each polynomial, irreducible polynomial will associate a variety Ci, and the denominator can be associated to the union of all these irreducible component Ci. Okay? Now, what happens when I take a residue? I would like to just draw an example to kind of simply visualize what's going on. So let's take like a cubic curve that self-intersect and a line. And let's say that the denominator of our differential form is the product of this polynomial corresponding to the self-intersecting cubic and the line. So these curves intersect into 3 points. Now, if you take a residue of a form that is singular on these 2 lines, you will see that if you take for a generic numerator, let's say, for example, that we fix the numerator to be 1. It will not be a projective form, but let's forget about it for a sec. We take a residue on the cubic, you will find that the residue will have 3 singularities. The singularities will be on these 2 points and in the self-intersecting points. If I take a residue on the line, I will get a form that has 2 singularities, where these 2 intersection. So what is a kind of a unifying description of these points? Well, these points are the singular point of the curve that is given by the union of the line and the cubic. So these points are the points where the tangent space of this curve, it is not defined, let's say. It was degenerate. So here the tangent space is like given by this line. The tangent space here is the line itself. And when we get to this point here, there is a singularity. So the nice thing, though, is that if we are working with varieties, this condition that the Jacobian drop rank, that is the tangent space is not defined, is just a system of polynomial equation again. So the region where this curve is singular, it's again a variety, and it's called, so the statement is that the singular locus of C is a variety. And this is a theorem in algebraic geometry. And if the field where these things are defined is closed, we also have that there is some even further simplification. That is that the singular region can always be described in these two types of singularities. They can either emerge from the intersection of irreducible components of our variety. So like we have here, we have two polynomials. When the thing will be singular again? Well, when I put to 0 both of the two polynomial at the denominator. And they have this third type is when the curve itself, where I take the residue, it is singular, okay? So, so now my point is that if we want to visualize what are all the possible residue on this form, we can kind of draw a diagram where the first point is the form itself. Then we can write the irreducible components of his denominator. So I get here by taking a residue on C1, I get here, take a residue C2, and I can connect this to the subvarieties where I can take further residues. A2, now I have A3, and this guy have putative poles on all this thing, and I can draw this diagram. Now, each of the layer of this, this layer is given by the irreducible component of the singular variety of C. And the nice thing is that this is something that you can put on a computer. So you can take, for example, Macaulay 2, you take the denominator of your form, you compute what the singular variety is. It's just a system of polynomials. So in the language that Macaulay likes is an ideal. You say, Macaulay, compute the irreducible component, and will spit out for you these 3 points. Okay? And here I didn't have to choose any coordinate system to do this. I can do everything covariantly. And therefore, the statement is that, maybe I can erase something. Let's erase this. So we will call this the singularity poset. Now, residues, and when I say residue, I mean multivariate residues, iterated multivariate residues, are in correspondence with chains, that is, oriented path in the singularity poset. Let's say chains in the poset. Okay, so this I think is maybe isn't for sure nothing new, but I think it gives us a very systematic way of not missing. Like if I have a form and I want to compute all possible multi-residue, I don't want to miss any. How can I do that? I take Macaulay, I compute this stratification, I enumerate all the path, and then I can just take iterative residues corresponding to each of the path. Yes, so the numerator will determine what residues are 0 and which one are not, essentially. And also if you will have double poles or you will not have double poles, let's say. This is what the residue can change, but the residue can never give you more singularity. This is essentially the statement. Whatever is the residue, it will not give you more possible residue location. You can just kill some singularity, but cannot generate new one. Okay. So if I have a specific form, then it's very interesting to see what are the non-vanishing residues. So there will be a subset of this path that will be non-zero. And then a more refined question is, what are the relation between these residues. So this residue will be sum of residue that will be equal to 0, and some that will not be. Okay, so of course I hope you were a bit surprised when I tell you like that the box have 100 different multi-residue. Usually looks like there are a handful, but this is because most of them are related to each other trivially. Like if I take a residue in, I have the form before, I take a residue in X and then in Y, it is equal to minus the residue in Y and X. So there is a very simple relation between the two, and if I mod by this relation, of course, I get a much smaller number of residue. So this in cohomology is called what is the cohomology ring of your form. So you'll have your form will have a bunch of residue. Not all of them will be independent. You want also to compute the relation. And one nice thing that positive geometry, okay. Sorry, Andrew? Yeah, so it's in general like a complicated thing to find the relation, to know in advance what are the relation between the residues. So like in maximal residue, for example, you can use some technology, but just for hyperplane arrangement, this is a kind of field of mathematics that is its own name that I forgot. But essentially, if you want, like in a hyperplane arrangement, to know all the relation between all possible residues, there is some theorem and things that tell you how to deal, what is the group of this residue form, what are the relations. It's not obvious. Like, you know, like it's just because each multi-residue corresponds to a path. So let me show you this then, in fact. Let's see if this thing works. So this is the stratification of GR2,4. So it's the stratification of this of the box, okay? And the point here is that we have, I remember, I think is like 4, you know, possible residue at codimension 1. Then you have like 6. I should have written it somewhere here. Oh yes, 4, 10, 12, 6. You know, here we have like 2 possible residue here, 3 possible residue here, okay? Here we have 4, 10, 12, 6, okay? Yeah. So at the beginning you have 4 guys, then you have 6 guys. They're connected in some particular way. And then to each path in this diagram, it corresponds to multiple residue, right? And you can see that because these numbers are small, but not super small, you will have a lot of path in this oriented graph. 10 is like that this at codimension, so this is codimension 1, this is codimension 2, and this is codimension 3, and this is codimension 4. That is, these varieties are points, right? This space is 4-dimensional, x, y, w, z, right? Good. So you see, like even in this simple case, like you need to organize the information somehow. And here I show like a way in which this mathematician organized the information is through Schubert calculus. So each of these varieties are Schubert varieties, and they can be described using like saying essentially how they intersect, or what is exactly the dimension of the intersection with some hyperplanes. And there, I mean, I don't really want to spend too much time on this, but let's say that VI, it means that our line in L4 will pass through the point VI. PI, it means that our line will be contained in a certain plane. If I have 2 lines, it means that our line intersects 2 lines, and so on and so forth. So when you have 2 condition is the product of the 2 things. So our line will pass through the vertex VI and the vertex VJ. And in this way, I can classify what are all the variety in my poset and kind of see which one are have the same structure and which one are not. So in the case of the 1-loop amplituhedron and the 2-loop amplituhedron, I can say that we never have self-intersecting singularity. We just have intersection, and this is very good news because these are very subtle objects and it's hard to take residues on there, and this makes computation much easier. Okay, so one last comment. Schubert calculus not only allow to label your varieties, but it's kind of work out for you also all the factorization property into prime. I told you that the steps are, I compute the singular variety, and then I have to decompose it into prime varieties, right? So in irreducible polynomials. This technology do everything for you, so in principle, you could also not use in Macaulay. So let's go now to the two-loop case. And with the Macaulay. So to do with Macaulay, if you brute force the problem, it's not efficient. You have the way we do it, but like if I go to one loop, I can brute force it. Two loop, if you brute force it, will never terminate. So here you have to be smart and use the symmetries of the problem first of all. So we have a dihedral symmetry of the amplitude, and we have a symmetry between the two loops. The loops is symmetric. And if you mod out by the two symmetry, that's already get you to the end. And then there is some other subtle improvement that you can do, but these are the main one, let's say. Okay, so let me show you a bit what happens at two loops. Let me comment that this another nice feature of this stratification is that it's agnostic to the numerator. So it kind of, you can also use it to study like the space of forms that have the same pole structure. And I'm not talking about that today, but I think that's also an interesting avenue. Like, it kind of contain a lot of information. Okay, two loop. So two loop, the form is a sum of double box, right? And how is the denominator? Well, is the product of the two one loop denominator. So it has this AB, I plus 1. There is another loop that I will call CD, I plus 1. And then there is a new denominator that is A, B, C, D. Okay, is this determinant? This, the computer don't know what it is as a polynomial in a variety, so you have to write it in terms of Plucker variables. And you can do it in this way. So it is essentially a Plucker, is the Plucker relation where in the second bracket you put CD instead of AB. So we have AB 2, 3, AB 1, 4, minus AB 1, 3, CD 2, 4, plus symmetric. So you see that the left-hand side is symmetric in ABCD, the right-hand side is better be as well symmetric. So what's the novelty here? This is at degree 2 polynomials in the Plucker, while these things were degree 1 polynomials in the Plucker. So new things can happen thanks to the fact that this variety is a bit less trivial. So what we see here is the multiplicity of all like the element in this singular poset, and you can see that the number grows extremely quickly. So I just want to show you one of these kind of levels in the stratification. So this is codimension tree, and this is because it's the first time that something kind of new appear, and you can see the first boundary that were missed in the previous analysis. So the first group are just boundaries that are all present in the one loop time one loop amplitude stratification. So there are all boundaries that you can kind of know from the one loop analysis that will be there. Then you have some new boundaries that are not in the product stratification, but they are extremely trivial. So essentially, there are some boundaries, let's say when, I don't know, AB 1, 2 is equal to 0, CD 3, 4 is equal to 0, and then the mutual positivity condition is equal to 0. And I say that they are trivial in the sense that there is no unexpected factorization of polynomials. While these two boundaries here are like the new one that were missed. And I try to show you why they're interesting from the point of view of both what happens from the point of view of the residue and the point of view of the geometry. So from the point of view of the residue, this comes from the fact that if you have two lines that intersect the same line, okay, in this case, this will be the line AB, this will be CD, this will be the line Z1, Z2, right? And now I want to set the bracket ABCD to 0. This geometrically means that these two lines intersect. This can happen in two different possible ways. What it means algebraically, it means that this polynomial here factorized in the product of 2-degree-1 polynomials. So if I set to 0 AB12 and also CD12, this polynomial will factorize in the product of 2. So what are these two possibilities? Well, three lines can intersect if they all lie on the same plane or if they all intersect in the same point. You have these two possibilities. It's something that was well known, but the authors of the previous paper actually they had some very nice technique. They were very efficient. They went up to 4 points, but because their technique were kind of fancy and not kind of brute force like our approach, this type of subtlety were missed. And geometrically, the interesting fact is that when you look at the geometry, you have these 2 points on this line. And this point on this line, this is an oriented line, so it's the notion of ordering of this intersection point on the line. And in this geometry, actually, the point can come in any order, right? So it looks like there is no boundary when these 2 points collide. But if you observe like how the orientation is induced, you will find that the configuration where the 2 points are in this order, okay, let's say like A1, C1 has a certain orientation. If they are in the other order, they have a different orientation. So let's say that the geometry looks like the example I showed you at the beginning. These 2 points, this geometry can be recasted as 2 segments with opposite orientation, and this singularity is what we call an internal boundary. So from the point of view of the geometry, these two, when you cross this variety, you are still inside of the geometry, but you have 2 opposite orientation, and these are discontinuity of the orientation. Okay, I know that might not be super precise, but this is essentially what happened. Okay, any question on this? This one? These two? The bottom. Okay, so like. So you remember, like here there is no integration contour. This is just your differential form, and you are kind of exploring the whole possible domain. It's like if you were integrating on the whole space, right? Yes. So if you are integrating on the whole space, you will definitely find these singularities. This, and this. Yes. Yes, yes. Well, like this is what you mean by gauge in this context, because this is an amplitude, so it is gauge invariant. Right, but the nice thing is that these are all residues of the amplitude, so residues of the amplitude are also gauge invariant. So if you have a form that drop this boundary, you have to ask like, what is the space of possible amplitude integrand that do not have this point, you should go back to the beginning like, okay, I want this denominator, I want this pole, I write an ansatz for the numerator, and then I start taking residue and I impose that that residue, it will be equal to 0, right? And you can do this exercise, and this is something that people do, and try to see what you get out of it. In this case, I believe you will get that there is just trivial solution. So you either, if you have this bracket, you will have that residue to be non-vanishing. But I've not done the exercise. I cannot tell for sure. But it's what I meant at the beginning when I was saying like this stratification posit has a lot of information. You can use it essentially for bootstrap thing, like write a numerator, then put some constraint that you like on possible residues and see what you get. If you get some consistent answer, or you get just no solution for it. You're welcome. So now I would like to, so for the moment I've talked about these residues, and I don't think I will, we'll see if I will have time to talk about boundaries, but if you believe that the amplituhedron is really the positive geometry whose canonical form giving this amplitude, well, essentially you can be happy with everything you get from residue. So everything, all the relation, all the thing that will be computed for residue will apply to boundaries. A different thing that I would like to talk now is about the topology of this geometry, the amplituhedron. So residues are not something topological. So it's very important with residues, the geometry. Like, I can give you this simple example. If I have a geometry whose boundary is a circle and 2 lines, okay? Topologically, like these 2 segments here are like 2 completely independent things. And to be honest, like, just if you care about these points, they're 2 separate things. If you don't care about, if you're truly topological, this is just, the boundary of this thing is again just a ball. So there is no notion of this, this division of the boundary into subvarieties. But even more strikingly, at least to me, is that if you take a residue on the circle, you will get the sum of the canonical form of these 2 segments here. There is no way with residue to get just this segment or just this other segment, because it's a very important thing that these 2 sits on the same variety. So geometry for residues and for positive geometry is very important. And of course, topology a lot is lost. And the main point I want to say is, like, if you compute the boundary stratification of the amplituhedron in the way I described, like this boundary stratification of residues, you could be tempted to say that the Euler characteristic is the alternating sum of the number of boundary that you find at each codimension, right? So for a square, right here, we have that the Euler characteristic, usually we say we have 1 facet, then we have 4 things of codimension 1, we have 4 things of codimension 2, the vertices. We take the alternating sum, 1 minus 4 plus 4, and we get 1, and we say height is equal to 1. But if you do that with boundaries, this not really give you the Euler characteristic of the amplituhedron. And so let's see so what's the proper way of computing the Euler characteristic? The answer is, and I will go through some of the steps for the amplituhedron, is to give what is called a CW structure for your set. So the way that mathematician thinks of computing topological invariants most of the time in practice is essentially give a triangulation to your space. Then you know very well, like, what are the boundaries of triangle, you know how they glue together, and then you compute all topological invariants that you want. It happens that for some spaces, like the Grossmanian, you cannot really triangulate the space with simplices, not even deforming them. So the positive Grossmanian, for example, is not what is called a simplicial complex. You need some bit more general definition that is this CW complex. But the idea is again the same, like you triangulate the space into region that are nicely behaved. You know how they glue together, and then you extract all the information you want from the geometry. Okay, so what's the key idea with these CW complexes? So I can show you in an example and see, for example, why being naive in this example failed to give you the right value of the Euler characteristic. So here we will be tempted to say, okay, I have one region, codimension 0, again 8 at codimension 1, that is all these segments, and 8 at codimension 2, therefore the Euler characteristic is 1. But this is wrong, and the idea is that the thing that we are there is one element that we are counting here, that is this bidimensional donut, that has a hole. So it is not homomorphic to an open ball. This would be the key condition. So how we can solve this? Well, we can add a kind of a spurious boundary to the geometry. So we do almost a subdivision. We are really not any subdivision because the regions are the same. But now the counting changed. So I have one region now, but this region now, the interior, I can unfold it and it's kind of a rectangle. So it kind of nicely behave. Now I have one extra codimension 1 thing, so I get a 9 here, right? So if I take the alternating sum, depending on how I take the sum, I will get either 0 or 2. And this is the correct result. So it happens that the interior of the amplituhedron is not homomorphic to an open ball. And so we have something very similar to do. And so if we just count boundary, we get the wrong result. We need to subdivide the space into regions which are homomorphic to open ball. How we can see this? Okay, so let's see how much. Yeah, I do have time. We'll take a parameterization. Parameterization should not be thrown out of the window. They are very important to do computation, especially in the interior of the geometry. The interior can always be nicely covered, essentially. So maybe I should also erase that is old. Okay. So we use the same, we have 2 loops now. We use the same parameterization of the 1 loop case for the first loop. So this time I will call the loop A1, B1 and A2, B2. And the parameterization was 1, X1, 0, W1, 0, Y1, 1, Z. So these parameterizations are not random, are inspired by the geometry, but if you have time later and ask me about it, one can derive systematically these parameterizations. And the other one is x1 plus x2. So we take like, well, maybe, yeah. A nicer way of writing this is actually A1, P1, plus, and then we write exactly the same matrix here. 1, x2, 0, w2, 0, y2, 0, z2. Sorry, and here there is a minus. That is irrelevant for forms, but is kind of useful for geometries. Okay, so how is the amplituhedron, the interior of the amplituhedron described in these coordinates? It is very simple. So the first set, the first loop inequalities are that x1, w1, y1, z1 must all be bigger than 0. So it's just a quadrant or in higher dimension. Then the inequalities of the second guys are x2 must be bigger than minus x1. And same for all of this. Well, w2 must be bigger than minus w1. y2 must be bigger than minus w1. And z2 must be bigger than minus z1. Okay. And then we have the degree 2 polynomial. That is x2, z2 plus w2, y2 bigger than 0. And already in the second paper of the amplituhedron, they suggest to represent this interior. They have a different coordinates, but similar. And you can think this relation as a scalar product. So I have x2, w2, dot z2, w1, y1, y2, sorry, bigger than 0. So I have two vectors, let's say a and b, and I have a scalar product which must be positive. Therefore, you can make the following. We can draw our geometry and get some intuition. And again, in different coordinates, this is something that was suggested to me by Thomas Lamb. So we have set two vectors, b and a, right? Here we have the variable xi and zi, and here we have the variable wi and yi. You know, this is an 8-dimensional geometry. I think it's quite nice that we can represent it in 2 dimensions. Then we have two boundaries for this guy, for the second loop, that are z1, minus z1 and minus x1. So we said that the coordinate of the second loop must be always bigger than minus z1 and minus x1. So they must be on the right-hand side of these two lines, these two vectors. And then this is the second row of inequalities. Then we have other two linear boundaries given by minus w1 and minus y1, right? So each of these vectors is closed in an infinite square. And then this angle, you know, must be smaller than 180, of 90. The scalar product must be positive. So let's say if I fix A, B cannot go over this line here. So what I notice here now is that firstly, this space is connected. So I can always take this line and push them very, very far. Then I will be able to rotate these two vectors in any way I like. Therefore, starting with a random configuration, the geometry is given by the position of the lines and the position of the vectors. Starting from any configuration of the line and the vectors, I can always move the lines far away and rotate the vectors in a certain position, canonical position. So from any point, this is the statement that in any point of the amplituhedron, I have a path that goes to another point of the amplituhedron. Great, so the space is connected. But let's now see that the fundamental group of this interior is not trivial, but is actually Z. So there is a non-contractible loop inside of this space. And this is very easy to see because I can push this line far away. I can fix the angle between A and B, and then consider the angle respect to the axis, right? And make a rotation. So I can define a circle in the space. And then notice, forget about other degrees of freedom for a moment, but let's think about just the length, the radius of this circle. Well, this circle cannot be really contracted to a 0 radius, because if the radius is 0, the scalar product between the two vectors will be 0, right? So then to actually prove that the fundamental group is Z, you have to show that you know, any circle essentially of this type in your geometry can be always continuously deformed into this. But I see that, I think, like, without going to the detail, this is pretty convincing that the interior of the amplituhedron, there are non-contractible loops, okay? So what it means if the fundamental group, you know, fundamental group is Z. When we count for the Euler characteristic, this is not one region. We have to subdivide our space into regions that have a fundamental group that is trivial. So how we can do that? Well, the intuition is that we have subdivided space into two regions, such that any of these loop will be half contained in one region and half contained in the other, such that if you have, for example, let's say that you have a circle without a point in the center, the fundamental group is non-trivial. Now, if you take a line that passed through this point, well, now this space only have contractible loops. This has only contractible loops. The intuition is that if you take any non-contractible loops, we'll have a non-zero intersection between the two spaces. So that's why what we did for the two-loop amplituhedron is to take two regions here. One is x2 bigger than bigger than 0, for example, and x2 smaller than 0. If we take these two regions, if you take this region, for example, then you will not be able to perform a circle around the origin anymore. And therefore, in this region, let's say, x2 bigger than 0, you will see that the interior of the amplituhedron, at least, doesn't have any non-contractible loops. Now, how you show that is homomorphic to a ball? Well, you have to really show that this space can be written as a fibration of open segments. If a space is written as a fibration of spaces that are contractible and never degenerate, then it means that it's homomorphic to a ball, right? So for example, a square, you can show it's homomorphic to a ball, the interior of the square, because it's a product of two open segments. It's a fibration of a segment on top of a segment, and this is the strategy that we are employing at the moment to subdivide the amplituhedron into some region, and then show that the boundary of each of these regions are homomorphic to an open ball. So the idea, so the last point that I was to finish is that to compute residues, we computed the stratification of the boundaries of the two-loop amplituhedron or the poles of the two-loop amplitude. If we then care about the topology, we are forced to add a spurious boundary and study the stratification with a spurious boundary. This is what we are doing at the moment. The things are that we don't see any octuple, but unfortunately I cannot present you the final result yet. But we are the key thing now. Before was Macaulay. Let's say that the key thing is now is maple cylindrical algebraic cylindrical decomposition. Cylindrical decomposition algorithm. Algebraic cylindrical decomposition. And that algorithm maple essentially exactly allows you to do everything systematically and not forget about anything like Macaulay was doing for the stratification. Thank you. Right. Right. Right, right. So that's the starting point. So the starting point, that computation is this. Like if you have a quadrilateral, okay, your boundaries are these 4 lines. What are those numbers in this case? Those numbers are the fact that you have 4 codimension 1 boundary, and then you will have 5 codimension 2 thing. Okay, so that is that. So it doesn't know anything about the fact that you have a square. This is just an algebraic. That's also called the algebraic stratification. It doesn't know about the interior. Then what we're doing is take a refinement of that. So then for each of those variety, I didn't have time to say that, but like for each of those elements, then you will have to take the intersection between between those variety and your geometry. So in this case, you will get these 4 segments, for example, and these 4 points, and you will not get this point, okay? So you get a refinement of the stratification that we call the real stratification, and then boundaries of your geometries will be path in the real stratification. So remember, like residues were path in the algebraic stratification, okay? Boundaries are in correspondence with residues, so they are also path in the stratification, right? But it's clear that any path that passes through this point will have a 0 residue because the geometry is degenerate there. Really the support of the geometry, whatever is the orientation, is 0. So yes, but I don't have the. We have the computation up to codimension 3. We're finishing it, but essentially we do. Yes, we have an algorithm to do it, and we are doing it. Right. So in this case, I mean, the nice thing. So in general, boundaries and residues are very subtle, as you said. In this case, most subtleties do not appear. Like we can compute everything. This is the point. It's just a matter of organize. You see, there is a lot of information. What we are working on is organizing the information nicely, having something like this language when you can package all the information and kind of understand a bit of the structure. But there is no multi-residue that we are struggling to compute or boundary that we struggle to compute. Yes, this last 2. Yes. Yes. They are part of the geometry. They have non-trivial residues. Yes. So they are very important then for also the other characteristic.